So we have now a method to follow a branch along, even if it goes around the saddle node bifurcation, around the fold. And so we have to think about other bifurcations. So the idea is that we have, if this is our bifurcation parameter lambda, and that's our solution x, we have some branch, and then at some point it goes undergoes a bifurcation. Let's say pitchfork transcritical bifurcation. It's easier to draw. Okay, so what we'd like to do is mainly we want to identify this branch and then have the choice of following it along instead of going the original branch, right? So maybe I should emphasize that first. Our branch following method always takes a tangent along the branch we have right now. And as we do that, it will not notice at all that there's a transcritical bifurcation because this tangent just continues along these lines. It will just not notice it. So in order to follow this branch or this branch, we have to first identify that bifurcation, and then we have to switch the branch. So it's two tasks that we have to do. Okay, so how can we identify it? Well, we need sort of a test function. So we need to identify bifurcation. And for that, we need some kind of a test function that we evaluate. And if it indicates whether there's a bifurcation or not. So it could be a test function which depends on the solution and our bifurcation parameter. And so if we had a steady bifurcation, which is characterized by a zero eigenvalue, then we could say, well, the determinant of the Jacobian would be a good test function because that would have to be zero at the bifurcation point. So let me call that bifurcation point lambda c, so that we would have at lambda c, the determinant would be zero. We haven't talked about bifurcation with complex eigenvalues yet, but there could also be an instability involving complex eigenvalues, which would be a Hopf bifurcation, or let's just call it oscillatory right now. In that case, there are two eigenvalues, which are always a complex pair, and they go across the imaginary axis. The real part is zero. So we could measure sort of always the sum of two eigenvalues. You know, if they come in pairs, then this guy would be zero if mu I and mu I plus 1 were purely imaginary and complex conjugate of each other. So if we simply take that product here over all the eigenvalues, we would also have some number which would be zero at the bifurcation point. There are other test functions that one can come up with which may be more efficient. For instance, this, like here, calculating all the eigenvalues of this problem is actually quite expensive. I mean, in all these analyses, you have to remember, we're not looking at just two ODEs. We may well be looking at bifurcations in a PDE, where the number of the degrees of freedom is actually the number of grid points that you have. And it could be 100, could be 1,000. I mean, so these problems could be quite large. And so we can't just assume that you can calculate all the eigenvalues all the time. Okay, so there are additional test functions which one can look up or discuss, but let's just leave it at that for now, that we need to have a test function that tells us where the bifurcation is, and then we can identify that bifurcation point. Well, we'll do that at discrete points in lambda, right? So we're marching along like that. And so most likely we will have, therefore, a data point here and maybe a data point here. And so we could then actually use linear interpolation to get at the bifurcation value more precisely. So if this was, so this would be my lambda c here. This would be lambda n plus 1. This would be lambda n. And essentially, you can just do linear interpolation. This is lambda n. This is lambda n plus 1. And we have maybe here this test function. And so that test function was measured here, and it was measured here. And so assuming this is a smooth function, which it most likely will be, then we just interpolate linearly between these 2 points. And by simple geometry, find out what this value is. I guess I don't have to write it down. It's in the notes. It's very straightforward. But the point is that it may be more efficient to just calculate at equidistant points in lambda and then interpolate between them. And then we get the bifurcation point. And if we need the solution at that point too, we could also interpolate x from here and x from here and get an x at the bifurcation point more precisely. You could, if you wanted, could also say, well, once we have that, we can predict where the bifurcation point is and then make a step to that point here and then calculate the solution there. That would be quite precise, but it would be also costly. So one has to think about these things. Well, if you really need the bifurcation point precisely, which sometimes is the case, then this procedure will not be good enough. And so you really would like to use a Newton method then to get that bifurcation point. And so, so we need to write down the conditions for that bifurcation to occur and see that we can solve that with a Newton equation, with a Newton iteration. So we come up with some function t, which will depend on, well, what are we varying? We're varying lambda, we're varying x. So that's this variable y, where y is equal to x comma lambda. Well, that's what it looks like initially, but we'll see. We'll have to extend that. But so what is the condition? We want to have that this is 0 at the bifurcation point. So of course, we need to have that the solution that x satisfies the fixed point equation. So this has to be 0, f has to be 0. But it also has to be a bifurcation point, so that means the Jacobian has to be 0. Well, not the Jacobian has to be 0. It has to have a 0 eigenvalue. So that means we need to calculate actually an eigenvector with eigenvalue 0. So we need to find, for our Jacobian, we need to find a phi such that this phi f times phi is 0. And that sounds fine. But it can't be the full story because this equation, of course, is always valid. Satisfied with phi equals 0, which we don't want, right? So we need to have that phi is actually not 0 itself. So we could set its norm to some non-zero value. We say its norm has to be 1. And so now you see what we also need in addition to x and lambda, we need to have that phi, right? So we need to calculate phi and lambda. So this y is actually a relatively large vector. This is actually 2n+1 dimensional, right? So that means this becomes kind of slow because instead of just solving n differential, not differential equations, n equations, we have 2n+1 equations. Okay, but in principle, this is amenable to a Newton analysis. So, run your Newton on it. Of course, for the Newton to be successful, you have to have a good starting point. So let's see. A good starting point is we need a good starting point for x. Well, as we said, we can get a relatively good estimate for x from our calculations that we've done so far. We calculate the solution at this point, and at this point, then we can take the linear interpolation, so we get x relatively good at the bifurcation point. And same thing is true for lambda. So we have good estimates for x, starting points. With good estimates as starting points for x, and lambda. What about phi? Well, that's a little different because we can't calculate phi at lambda n or lambda n+1 because at neither of these points, the Jacobian has a 0 eigenvalue. There is no such eigenvector with 0 eigenvalue. So what one can do instead, one doesn't solve the equation as written here, but rather one eliminates one of the rows and replaces that by simply a normalization condition. And once you eliminate that row, then you can solve the equation. So effectively, in picture, so to speak, if we have fx, but we replaced that by a matrix, which is essentially fx, except for one row. Let me indicate that like that. So in that row, we take all the fx's away, and we replace it by 0 except for 1, 1, maybe in the kth position. And we solve the equation, this equation, right? Phi equals not 0, but rather what we want to do is we want to require that the kth component of phi is 1. So we need to set a 1 here, and all the others are 0. And if this was the lth row that we replaced, then this will be also in the lth row. So that's the equation you can always solve. And we can show that if you're really close to the bifurcation point, meaning fx, the Jacobian is, when you go to the bifurcation point, this is a good starting point, a good guess for the vector phi. Okay, so that means we now have a reasonable good way to even calculate the bifurcation point and the solution at the bifurcation point quite precisely. So then we need to switch the branch. So let me make a new picture. So the picture is now we have still our good old bifurcation diagram. And we have this one branch here. And let me call that the known branch. It's the calculations X that we're doing by just doing our branch continuation. And at that bifurcation point, which I assumed right now was transcritical, just so I can draw something specific, we have another branch showing up, and we want to switch to that branch. So how could we do that? Well, in principle, we can calculate, if we knew this tangent here, then we could simply start along this tangent and march out and then follow that branch and also backward. So that's in principle possible, just like we do this, calculate this branch, this tangent. But it turns out to be relatively expensive because you have to calculate second derivatives, and that's quite expensive, and you have to have the bifurcation point very, very precise. So that turns out to be not very practical. So alternatively, what could you do? Well, let's first mark again what we know. We have, we are at a point here, say, that's our point lambda, where we actually are, and we have the solution here, x of lambda. I just noticed this is drawn awkwardly. Let me draw that branch here differently, just so we have, it's easier to draw. So I want to have this like that. Okay. So I'm aiming for a solution on this branch, right? So I'm aiming sort of here. Now, as we've seen from our weakly nonlinear analysis, if we're close to the bifurcation point, then the instability that makes this branch unstable, let's say it's stable here, goes unstable here, the instability that kicks in there is associated with an eigenvector, and that eigenvector is actually essentially the difference between these two solutions very close to the bifurcation point. Now that eigenvector we can calculate. We just said how to calculate. That's this phi we just said how we calculate it. And so essentially we have a guess as to how to get from this known branch to the unknown branch. It's essentially in the direction of this eigenvector phi. But we need to know how far to go, right? The Newton really wants to have a good approximation, so we need to know how far to go. So we sort of need that distance, it seems. So we have a distance here, some distance vector. And How do we know how far to go? Now, again, it turns out to not be so easy to do, to calculate that, because, again, you would need second order derivatives, which are hard to calculate if, again, this is this large system. So let's just sketch that very simply to see why we would need these second derivatives. If you just did your scalar case, where we have 0 is equal to f of x and lambda, right? That is f of, let's assume our fixed point is at 0. But I keep lambda c here for a reason that becomes apparent in a second, plus df by dx evaluated at 0 and lambda c times x plus df by d lambda times lambda minus lambda c plus 1/2 df squared by dx squared x squared plus more and more. So the distance that we're talking about here is the distance between the base solution, which in this simple calculation I'm thinking is 0, and the new solution, which in this case is simply x. And so what we would need is an estimate for this distance. We would need an estimate for x. And you see, in order to get an estimate for x, again, there's the second derivative I mentioned that we need to know in order to estimate x. Estimate because the higher order terms are there and we don't know them. But even if for the estimate, we would need those second derivatives. And we need to know lambda minus lambda c, which means we need to know lambda c, the bifurcation point, quite precisely too. So that's not so good. So an alternative strategy which works better is to say, well, I'm going to pick a fixed distance here. I'm going to go a certain distance, but I don't insist on that the lambda is the same value. So I allow lambda to vary. So to speak, let me maybe do that in a different color. Let's see. So if we had a magenta, so if we had picked maybe the distance only to here, right? So say I pick an arbitrary number, small distance, and I pick it here, and which is not enough for this lambda value, but there's another lambda value for which actually this distance would be okay. And so the lambda, I would want to go with lambda to that value. So in other words, instead of having the distance being the unknown, it's the lambda that's unknown and the distance is fixed. And I keep the distance fixed. This has also the following advantage. What you really don't want to have happen is that you make that prediction here, so to speak, which you then correct by going over here, say, but you make prediction and then the correction just gets you back to the same branch here. So if you insist that the distance between the true solution, the unknown solution and the known solution is the same as your initial distance that you picked, then you can't go back to the original branch because you have a fixed distance. And so this would mean that, say if you pick this distance initially and you insist that the Newton iteration that eventually gets you to the right lambda value has such that the distance between the solutions remains the same as this distance, well, that would mean that you have to calculate, let's first eyeball it where we would end up. This is this distance, so that would be about here and here, right? So, so you would actually follow this branch, like, I shouldn't say it this way. You would end up here and here, and you would be guaranteed that they're not the same. That's very good, and you would get your real, the lambda value that goes along with it. The drawback of that is that you have to calculate both the solution that your branch that you've already calculated, and you have to recalculate it, and you have to calculate a new one. Well, the new one, of course, you have to calculate. But that's a good way to do it. We can say about something another way in a second, but let's first write down how we would actually implement this part. So Okay, let's see. We need to start, we have a solution x of lambda. And that should be close enough to the bifurcation point, right? If you're far away from the bifurcation point, all these guesses are pretty bad. So x is close to the bifurcation point. And now when we want to calculate, let's call that branch here z, the unknown branch is called z. And so we say, well, z, our estimate for z, which would be the initial point for the Newton, our estimate for z would be x plus some distance, which we pick is a delta, times the vector that gets us, that's associated with the instability here, right? And okay. So practically, this is a more practical thing, but let's just say it. We calculate this phi here in this way where we actually fixed the kth component, phi k, we fixed to 1, right? That's sort of what was achieved here. And so therefore, it's sort of natural to say, okay, let's do the same thing here, that we actually say that the kth component of z is given by the kth component of x plus some number delta. Okay. And then what else do we need? The other conditions are simply that we have f is satisfied by x. I mean, x needs to be on a branch. So f of x has to be equal to 0. Then we also need that f of z for that lambda value is also 0, right? We need two solutions at that same lambda value. And then finally, I just want to put this in a equals 0 kind of equation. So let me rather write it this way. This condition here, that the zk and the xk have a fixed distance, I would say that zk minus xk minus delta is equal to 0. This is good. It has one little glitch still. We don't know when we're on this branch, we don't know whether this other branch is above here or below here. There's no way of knowing. And so in order to accommodate that, we just say, well, we do two problems at the same time. Not at the same time, we do two problems. In one case, we require that the distance is plus delta. In the other case, we require the distance is minus delta. And that covers then both of these cases here. Oh. Okay, so that's how you can do it. And that works okay. But as I said, this is again a problem where you have actually two n+1 equations, which is a good large number. And so there's another way that you could do where you don't say that the distance between the distance between these, the z and the x stays the same, but rather you simply say that the z value doesn't change. Now, okay, in this graph, it's unfortunate. The z value happens to be the same, but that's not the condition we used. The condition we used was that this distance has to be the same as this distance. Maybe I should do that, make that clear in, in this magenta, ugly magenta color, that these two distances are the same. Alternatively, as I said, you could have the requirement that you make a guess for zk, like you say zk is equal to xk plus delta. And that's your initial guess. So that would be actually the zk bar, so to speak. And then in the Newton iteration, you allow zk not to change. So it has to stay the same. This doesn't guarantee that your z will be not on the y branch, because it could just so be that these branches, the shape of these branches are such that the y has a k component that becomes the same as the z has. But it's much faster because instead of, you don't have to recalculate the x anymore. You just calculate z when you have the condition instead. Let me put it next to it, although it's sort of ugly, but then we have a better comparison. So we would have the condition that f of z and lambda then has to be equal to 0, and zk minus zk bar is equal to 0, where zk bar is the initial guess for the zk component of z. So that's how you can actually then switch to the other branch. And once you are in the other branch, you can continue there, of course, as long as you please. One more little thing. As we said, it's very important to have good initial values. And so right now, the way I talked about it was that we assume we had just these golden values here, and we start from there. But we want to have good initial values also in the sense that we want to be close to the bifurcation point. And so therefore, again, if we have calculated the solution here and have calculated the solution here, we can again use a linear interpolation of this test function and calculate this quantity xi that we mentioned before. Where is it? Here, when we did. Well, I didn't define this xi, but when you calculate here this linear interpolation, we can calculate, use that here also, and get a good estimate for x at the bifurcation point. And also for phi, we can interpolate also this phi here from calculating a phi here, calculating a phi for the other lambda, and then take the interpolated value as a starting point for the calculation. Okay.